So, this is the theory portion of our DMS Geiger Counter Build class. For various reasons, we're not going to be able to do the actual construction today, and I'm going to have to coordinate with you to make sure that we set up a time when we can actually do it in the future, as opposed to people saying, oh no, I have a conflict. So as a general statement, what we talk about when we say radiation, there's lots of forms of radiation, including infrared, heat radiation, and so on. When we talk about radiation, we mean ionizing radiation. And ionizing radiation is so called because of its property of knocking electrons off of atoms and producing charged particles known as ions. Okay, how do we detect ionizing radiation? We detect it by its property of causing ionization. Typically, we use electric currents or electric charges. There are other methods. For example, in a scintillator, you apply a large electric voltage across a crystalline material, and the ionizing radiation causes a flash of light. That's fine. But you can, for example, your radioluminescent materials, if you ever saw a radium dial watch, tritium, whatever that is, that also is something where you have a solid material which emits light when it's ionized because the ions recombine, the electrons return to their atoms, and the energy involved is emitted as visible light. So that is a second way of measuring and detecting radiation. But the most common method that's used is by measuring some electrical property. So here we have a graph which shows, in a general way, a qualitative way really, the response of a gas to ionizing radiation. You put a voltage across it. So there are 5 regions marked across here. Region 1 is of no particular interest in practical terms. In region 1, the voltage is low, and so when ions are produced, what mostly happens is they recombine. Most of them disappear. So per event, the charge, which is transferred to the electrodes, is typically less than 1 unit electron charge. Then we have a plateau here. This is the region where ionization chambers operate. This is your smoke detector, typically. You have a moderate voltage. When ions are produced, they migrate to the 2 electrodes and conduct a small electric current, which is proportional to the amount of radiation being received. Region 3 is interesting. In here we begin to get cascade action, in which an ion which is produced knocks against other gas atoms and ionizes them in turn. Because it's receiving energy from the electric field, which is accelerating it, this allows it to knock on and produce additional ionization. A moving charge particle in general has the power to ionize other species, which is, of course, why alpha particles are so great at ionization. They're fast moving and they've got lots of charge. And of course, nearly the speed of light iron nuclei in cosmic rays are that much more powerful. So in this region, the amount of charge which comes off at the time of an ionization event is proportional to the energy in that ionization event. So you can actually build what's called a proportional counter, which distinguishes between different energies of radiation. That's pretty interesting, and it has some practical applications. Then we get into this region here which doesn't have a number, between 3 and 4. In this region, behavior is more nonlinear, so it's not really useful to people building instruments. And then we get to what's called the Geiger-Müller plateau. The Geiger-Müller plateau is a region of maybe 100 volts wide, in which every radiation event, every ionization event, every time a ray passes through the tube and produces ions, the electric field is high enough that those ions knock on enough other ions to saturate the tube. In other words, it acts like a switch, and a radiation event causes it to conduct briefly. That conduction then cuts off. That's important. In region 5, the conduction doesn't cut off. It just keeps going. That's a neon lamp. Turns out that trying to operate a Geiger tube as a neon lamp will burn it up very rapidly. Actually, glass Geiger tubes, if you keep them in the dark, you can actually watch the flashes of light which are emitted as the gas discharges in the tube, which is very cool. And some neon lamps do, in fact, include a small proportion of radioactive material to ensure that they light reliably when a voltage is applied across them. But yeah, this is the neon tube region. Do not run your Geiger counter in this region. It will burn the tube up. So when I talk about tubes, what am I talking about? Well, this is the tube we are going to be using. This is an STS-5. It is a Soviet-made tube. This one appears to be from 1965. It's okay, though. They don't go bad. According to the Centronics Introduction to Geiger Counters manual, basically the only time that a Geiger tube will go bad is if it's kept in an atmosphere of helium, because helium diffuses through, in this case, the steel wall of the tube. Steel, very thin steel being the most common material for Geiger tubes, diffuses through the steel wall and contaminates the gas inside, changing its ionization function. Assuming that these tubes were not kept in a balloon factory, they should be okay, right? So, how do you actually use a Geiger tube? So here we have a second diagram. Second diagram shows we put a high voltage, and then there's a large value resistor, megaohm value resistor, and then there's the tube itself, and then there's a smaller resistor. And convention is the small resistor is 1/45 the large resistor. That's just how you do it. Every Geiger counter you run into, the ratio between the two resistors will be as 1:45. So what happens? So an ionizing event, it's this tube. So this is the positive voltage. In this case, the spec sheet for this tube, which you can look at, but it's all in Russian, says 360 to 440 volts. In general, you operate right smack dab in the middle of that region. So we apply 400 volts up here. Now, of course, when the tube is not conducting, the megohm resistor does not drop any voltage. So the voltage here is 400 volts. The voltage here is circuit ground, right? Okay. What happens when it does conduct? Well, there's a voltage drop across the tube. It's like a diode or a neon lamp or any of these things. There's a voltage drop across the tube. In this case, it's what's known as the starting voltage, which, according to the spec sheet again, is 280 to 330 volts, depending on the tube. It's something that varies from tube to tube. We can assume it'll be right about in the middle of that range, so say 305 volts. So with 305 volts dropped across this tube, there's 95 volts left to be divided by these two resistors. And at the ratio of 45 to 1, the voltage which appears across the bottom resistor is just over 2 volts. Now, how does that happen? Well, again, we've got an avalanche phenomenon going on. So the ray enters the tube, produces an ion, that ion produces additional ions, and the current that passes through the tube increases very, very rapidly, which means that the voltage out here increases very, very rapidly. Then it trails off because the ions don't all move at the same speed, so there are slower moving ions which reach the electrodes, the outer tube being the negative electrode and a thin wire passing through the center being a positive electrode. There are slower moving ions which reach the electrodes more slowly. Now, in general, in one of these tubes, in addition to an inert gas, which is the main detection gas, there's a trace of a second gas, typically halogen, such as chlorine. And chlorine has a low ionization work function. And what that means is that it mops up, effectively, the ions which are left over towards the end here. It quenches the tube so that it stops conducting in a reliable way. But any additional events which occur during this period, since the tube is already discharged its charge, there's going to be a dead time here where you can't pick up another event. And so you do have to choose the correct tube for your application. If you're going to be exposing something to a very high radiation flux, you need a tube which is not sensitive, because in general, tubes will pick up only a fraction of the radiation which passes through them. Typical Geiger tube will generate one count for every 10 to 100 gamma rays which passes through the tube, because it's just a question of how much energy is deposited in the gas in the form of ionization. So, as a general rule, in a high radiation environment, you use a less sensitive tube, which maybe only generates one pulse for every 100 gamma rays. And in a low radiation environment, you use one which generates one pulse for every 10, let's say. But this is a reasonably sensitive tube. If you look on the internet, you'll find the STS-5 and its more recent equivalent, the SBM-20, are generally considered to run about 200 to 220 counts per minute, which is the usual unit for use with Geiger counters, counts per minute with just general background radiation. So if I were to apply 400 volts across here right now, which I could, you never know, I'm really like that, I would expect to get around 200 kicks in a minute. Okay, and this particular type of tube is good to much higher counting rates than that. For the purposes of this project, the counter we are going to build is only going to register up to 100,000 counts per minute. 100,000 per minute is probably as high as you need to go. Matter of fact, when it gets to 100,000 counts per minute, it's going to sound an alarm to tell you, back off. So the dead time in that case, if you think about it, 100,000 per minute is it's less than 2,000 per second. And so you're talking about half a millisecond of time on average between pulses. And this time here is typically in the nanoseconds, not even microseconds. So we should not be seeing any saturation effects. If you see saturation effects, again, you're too close to whatever it is, and you should get out of there. Okay, so I said we're going to be measuring counts per minute. How are we going to do that? The short answer is with a lovely trick of electronic circuitry. Now this is at the moment, this is the point at which I'm a little bit stalled for a kind of embarrassing reason. I thought I had everything lined up, then I realized I better not actually order several $100s worth of electronic parts until I was 100% sure of my circuit diagram, that I wouldn't have to buy additional parts or something like that. And I realized in order to be 100% sure of my circuit diagram, I needed to actually run through and make sure that the CPLD I want to use will actually do all the functions I need to implement in it. CPLD, of course, complex programmable logic device, and I'll explain why we need one of those. So, how do you calculate counts per minute? See, the thing is, of course, radioactive decay is a random process. So, if you have, say, 1,000 counts per minute, these are not going to occur regularly. Space intervals, they're going to occur bunched up with certain gaps in between. And so the usual method for measuring the frequency at which something occurs, for example, with a phase log loop, is not going to work at all. You try to feed a phase log loop from a Geiger counter, it'll go insane. So you're not going to use that technique. There's a technique which has been very successfully used in frequency counters for years, which is known as period inversion. So if you have events which occur in a kind of a non-standard way, you can use a reference which occurs in a very standard way. So to explain this more clearly, suppose that we have a clock signal, which is, say, 1 million counts per minute. And suppose that we're counting 100,000 counts per minute off of the tube. So we have a counter here which counts up 1 for every clock cycle that passes. And then we have a latch. And the Geiger tube triggers the latch. So whatever this count is up to when a radiation event occurs gets put on this latch and passed to what's called a rate multiplier. Now, a rate multiplier is an integrated circuit, typically, which has a curious function. It's got one input, which is a clock signal input, and it's got two outputs. The one output simply divides that clock signal by some number. In the case of the 7497 binary rate multiplier, it's divided by 64. The other output, in the case of a 7497, produces between 0 and 63 output pulses for every 64 output pulses which come in, or alternatively, for every one which goes out the other output. Now, what relevance is this? Well, suppose, again, we've got a clock of 1 million counts per minute, and 1 million clock cycles per minute. And it so happens that when a radiation event occurs, the number that the counter's got up to is 10. So it'll store 10 here, and so for every, say this is a divide by a million rate multiplier, for every million pulses which go in from the clock, you'll get 10 out. So if we have another register here, or another counter here, which has stored a value of 1 million, so every time a million clock pulses come in, it sends out 10 of them here, and we decrement this counter, count down. And so it takes quite a long time, obviously, but you get, for every 10 of those, of course, you get 1 to this up counter. And so by the time this gets to 0, you've got 100,000 in the up counter, which is, of course, a million divided by 10. And so 100,000 would go to the display. Now, clearly that's not actually practical, the way I've laid it out for you. If for no other reason than simply because to actually count that down would take 100,000 minutes, and nobody wants to wait that long for a radiation measurement. Generally not recommended, even if the battery would last that long. Okay. But there are a couple of tricks here. First is, we don't need 6 digits of precision. Really, you don't need 6 digits of precision. If we're going to count up to 100,000 counts per minute, you really only care what the top value 3 figures are. In fact, you probably can get away with 2 in a lot of circumstances. You care whether you're getting 1,000 or 10,000. You don't care so much about whether you're getting, 1,020 or 1,025. That doesn't really provide you with a lot of useful information in most circumstances. So, by working with 3 digits of precision, we can make the calculations a lot faster. What that does mean, however, is that we have to have 2 ranges, a ×1 range and a ×100 range. And this is easily implemented by dividing the input clock. So in the slow range, you take whatever the input clock frequency is, again, let's say 1 million counts per minute, and you divide that by 100. And so this register can be smaller. The number accumulated in it can be smaller, and the calculation can go faster. Not bad. Well, there has to be an automatic mechanism for switching between ranges, and that's fairly simple in concept, at least. Right. The idea is simply if you have it in the low range, for example, and this register gets up to a certain value and overflows, you switch to the high range. In the same way, if you're in the high range, and when the count comes in to stop the clock, as it were, the number in here is too small, it switches to the low range. And that's actually quite simple to implement with a couple of AND gates. Simply, you just have to figure out what the values are. And so in this case, what we would want is that when the count value passes 999, it switches to the ×100 range. So it switches, and you get 1,000. And then when it falls below 900, it switches to the ×1 range. Because if you happen to be right about at 1,000 counts per minute, you don't want to be switching back and forth all the time. That would be extremely annoying and make it almost useless as a measuring instrument, at least in that range. And again, you might be in that range for some reason. Again, this is not that hard to implement. I just have to be sure that I can fit all that logic on the CPLD without bringing in additional chips, so that if I do need additional chips, say for the 7-segment decoder to feed the display, that I can actually order them and make sure that there's traces for them on the circuit board. again, mea culpa, I was putting the cart before the horse. The other thing here is the time taken for, again, because these are stochastic events, right? These are not events which occur at a constant frequency. The time taken for one count is not really what we're interested in. We're interested in the average time over a number of counts. And so you can do it by various mechanisms, but I realized over, say, 32 counts, that 32 counts is a decent averaging period. At 100,000 counts per minute, 32 counts takes 19 milliseconds. At 200 counts per minute, which is a good average for background, 32 counts takes 9 seconds. So again, having this range switching mechanism is important because otherwise we'd have to accumulate really large numbers of clock pulses for the slow counting rates, or else seriously sacrifice precision for the high values. But in case my description of how this works was slightly unclear, feel free to ask any questions you have. Anyway, and then I have, this is just a drawing of what you can expect the counter to actually look like. This is about double size. Basically broad enough to hold a 9-volt battery, because the 9-volt battery is what is going to be providing the voltage. We have a switching regulator which produces 3.3 volts for the electronics, and a second switching regulator designed to charge a photographic flash capacitor, which provides the 400 volts for the tube. And actually a 33 microfarad photo flash capacitor, which is small for photo flash, but huge for this application, to the extent that, if the battery died, you probably wouldn't know about it for 10 minutes or so. That in fact, one of the things is that I'm going to have to get somebody to help me with this, because surface mount is not my forte, and the flash cap supply is a surface mount component. But that's going to be done before we start doing any assembly, because high voltage is dangerous. And I don't want anybody hurting themselves, much less me. But I don't want to be responsible for anybody getting a lead reversed or something and going, oopsie. As Steve Adams says, we don't want to pound on anybody's chest. We also don't want the flash cap capacitor to go bang. I don't know if you've ever seen what happens when a big old high voltage electrolytic goes bang, but I knew a guy in college who was electrical engineering with a creative arts minor, who made a short film which he used to simulate gunshots. Anyway, very simple user interface. This is just a knob down here on the bottom to make it easier to hold in your hand. Just a big knob. The knob has a screw thread stem which actually holds the upper and lower pieces of the case together. They snap together at the top here, and then they screw together at the bottom, and that allows you to unscrew the knob, and then you can open up the case to replace the battery. There's 2 slide switches, very simple. One of them turns it on. The other one gives you a choice. Do you want to hear audio, a click for every count passing through the tube? Very simple. There's just a little piezo buzzer type element. Its resonant frequency is 4 kilohertz. We're actually going to, 100,000 counts per minute, again, is less than 2 kilohertz. So it's going to be a distinct click for each sound rather than a continuous tone. And of course, the attack time is high enough, is short enough that that's going to have enough high frequencies to give it that definite click sound. So you get in the audio position, you get a click for every count that passes through the tube. And then there's the display, again, which will just show you the 3-digit display, or you put it in the center position, you get both sound and visual indications. And then there's a button. The button says count. You hold down that button, and instead of telling you counts per minute, it just starts from 0 and counts how many events occur while you're holding down the button, which could be useful in some situations. There's 2 indicator lamps. One is to show you what range it's in, so that's the times 100 indicator. The other is a super bright LED, actually, which would be the alarm indication. When it goes off scale high at 100,000 counts per minute, that light is going to come on and it's going to flash. And the other thing that's going to happen is that the piezo buzzer is going to start buzzing at 4 kilohertz frequency. And again, it's going to on and off, basically half second on, half second off, making a really ugly bleating sound so that you're not confused what's happening. And the only way you're going to get rid of that is by turning the detector off. That's going to be a latched up state, so that once it goes off scale high, it pegs, and to get rid of that indication, you're going to have to turn it off. Because again, 100,000 counts per minute is pretty hot. And if you are in that vicinity, you need to know about it in an unequivocal way. And that's actually, the alarm will sound even if you're in display only mode. That's going to be taken care of by separate circuitry so that it doesn't depend on you having the audio activated. You will hear it. And if we were to flip this over, it's actually blank on the back, but if we were to conceptually flip this over, you would find that there's simply a slot cut in the bottom to expose the tube. Because of course we don't want the tube sticking out because it's, well, you don't want it to be damaged. And so the casing is simply going to have a slot in the bottom with V-shaped, to like the hull of a ship inverted, but so that it exposes the tube to as much radiation without actually exposing it to danger or requiring you to have a cover over it. Some people's home build Geiger counter projects, they actually have the place the tube inside a plastic case, because plastic is not a very strong radiation absorber, and so you won't lose a lot that way. But because this tube is sensitive to both beta and gamma, you'll lose quite a bit of the beta in a reasonable thickness of plastic. And the casing is just going to be fabricated using filters here. Anyway, and then the other thing which I wanted to explain is, if you were here for Nuclear Science Day, you saw that I had a bowl full of these strange brown beads from Japan. These are marketed under the name of radium balls. What is their purpose? Remains to be determined. The Japanese, see, here in the United States, the Nuclear Regulatory Commission does not allow what they call frivolous uses of radioactivity. And so, for example, you can no longer buy what you could buy in the 30s, 40s, 50s, which were little glass beads with radioactive radioluminescent material inside. Originally it was radium and zinc sulfide, which you put on the end of the pull chains for your lamps so you could find your lamps in the dark. That's not legal anymore. In fact, the little, if you have you can buy on eBay little tritium lamp light element, which you can hang on your keychain. Technically, that's not legal, although people get away with it because the NRC doesn't really bother cracking down on people who have small quantities of tritium. And if you buy it from outside the U.S., they're not really going to open all your mail, generally speaking, just to see if there's anything radioactive in it. Powerfully radioactive parcels might, in principle, trip detectors somewhere, but again, I've never had a problem with that. This stuff is actually pretty hot, and I've not had a problem with that. So I'm going to measure out 5 grams. This is 100 grams here. I'm going to measure out 5 grams into each of these vials and put a radiation trefoil warning sticker on them and seal them tightly by putting glue all on the stopper. And then you will get a vial of radioactive material as a check source, but you are not going to get that vial, to check that your counter's working. You're not going to get that vial until you have the counter working. Because if you lose the vial, you're going to need the Geiger counter to find it again. But yeah, in Japan, these are sold to people who put them in their bath water. The theory being that natural mineral springs are always radioactive. This is just a fact. The soils, the world around us is radioactive. The groundwater is always at least slightly radioactive, and many volcanic hot springs in particular have wholly more radioactivity in them, typically in the form of dissolved radon, radio salts, than your ordinary well water. And so people like to think that if they add a little radioactivity to their water, that'll make it healthifying.
Maybe it's that Godzilla thing they have going on.
Anyway, this was common in the U.S. in the first half of the 20th century. In fact, you could buy a thing called a revigator, which is a water crock made with uranium ore, which would add radon to your drinking water. You can still find these on eBay under other weird stuff, really weird. Actually, I think there's also a category for quack medical products, which you can find them under sometimes too. If you just search for Revigator, you will find a device for adding radon to your drinking water in case you feel you don't have enough of that in your life. Again, in Japan, the regulations are different from what they are here. And as a result, you can buy this stuff quite freely. You go on Yahoo Auctions Japan, which the Japanese use the way we do eBay, and there is radioactive stuff all over the place. If you know how to write in Japanese, and you put in a little search bar for radium or anything like that, you will turn up lots of people selling this stuff. And it really is radioactive, as we demonstrated at the Nuclear Science Day. It's, pretty decent emitter. So, given that plastic doesn't absorb radiation particularly strongly, you will definitely be able to verify the function of your counter using that as a check source. So that's a brief overview. Again, if you want to take your Geiger tube home today, you may. Otherwise, I will keep them in the box here, which will hopefully keep them from getting lost or damaged. It's up to you. I do have, however, protective boxes if you do want to take it home. And the protective box is labeled with the, of course, in Cyrillic STS-5. The tube is made of steel, but that doesn't mean it's not delicate. If you rack it sharply across a hard surface, you might derange the wire inside. And the metal is quite thin, so you could, in principle at least, abuse it enough to bend and even break it, which would make it ineffective as a Geiger tube. So, questions? Okay.
So this plus, so that's anode.
Yeah.
Does that, okay. The wire, I assume there's one end's cathode, one end's anode.
Yes.
Does that mean that, does the side that has the plus on it, is that anode or?
Yes, this is the anode contact. The actual anode is a wire which runs through the center of the tube because, of course, the anode has plus 400 volts on it,
Right.
and you wouldn't want that to be exposed. So the shell is connected to the cathode, right? The shell is the cathode, which is connected to the ground electrode. The wire inside, and Pete Fish here had a photo he got online. The wire inside, which you can see in glass tubes, but not another one, obviously, is connected to the positive electrode. The wire inside is the anode. Again, the ends of the tube are going to be inside the casing, so that there's no danger of you touching the plus 400 volts, or not even you, but possibly your friends and family, small children, and pets, which again would not have a happy outcome.
So, as far as the CFPDs, we're planning on just burning them and giving them to us, or?
Yeah, the plan is once I validate the VHDL and make sure that I actually get the functions that I need, I'm going to get the CPLDs. I'm going to bring them up here and get Steve to just burn them, and then they're going to be. If I'm not badly mistaken in the choices that I've made, which is always possible in life, it's a 40-pin CPLD. We're going to have a socket. The biggest soldering job is going to be soldering that 40-pin socket down to the board, but it's much better than trying to handle the CPLD without a socket. I'm sorry, I believe in IC sockets. I am a strong believer in IC sockets, especially for a part that you really don't want to damage because it's customized.
True. Didn't want to say off camera. I think we may still have some spare CLPDs for the VHDL. VHDL class.
Yeah. These the ones I'm looking at, assuming I'm not completely wrong about the capability, are a Max 3064, which has twice the number of gates as the 7032s, which are being used in the VHDL class. and so it is a little more capable. Still is limited. I think they actually have Altera has a programming example where they use one of them as a 16-bit LED display driver. And so I'm thinking that I may actually have to use a separate LED driver in order to get the rate multiplier circuitry into the CPLD. For the reason that rate multipliers you can't get very easily anymore. Used to be, sometime in the past they were common. Nowadays they're not. Last time I bought rate multipliers, I had to get them, guess what? Soviet military surplus from Ukraine. I'm just buying Soviet military surplus stuff from Ukraine all day long. You know, little boxes marked electronic parts, and I haven't been arrested yet. So yeah, that's going to be the main thing. Is because originally I thought the CPLD would hold it all, and I was just going to push the button and buy the parts, and you know.
Yeah.
And then I looked up this programming example, and they had said, wait, okay, they're talking about how much of the chip you're using with just the LED display driver. I may have to go to an external LED display driver circuit, which, again, that's basically been the hold of it. So I mean, I got 2 or 3 things going on at the same time. My coin club has been really writing me to fix something on their website, which is badly broken. And so I need to do that, and I need to validate the HDL. So it's going to probably be 2 weeks, which would put us right smack dab onto the Thanksgiving weekend, where it's probably a bad idea to go out of doors because of all the demons on the roads. I mean, the only way I can describe it, people who apparently are possessed. You know, they will do anything, including mow down their own grandmothers, you know, just to save 5 cents on a plasma TV or whatever the reason is that they're out there. You know.
That's the weekend I think that was out at the how should we say, field.
Yeah, that sounds like a real good plan, actually. You know, you set off all the explosions you want that weekend that no one will even notice. So yeah, that's a précis of it. And if I can, since we had several people who wanted to be here who couldn't be, the video will actually be helpful if I can get it if you can post it on YouTube or something. I can send out a link to it. That'd be very helpful.
Okay.
Anyway, and like I say, I'll give you these so you can photograph them, so
Okay.
people can see the visual aids. And beyond that, anyway, any more questions? Anything else we want to get on the video?
Were you planning on making the VHDL code?
Yes, actually, I plan on putting up a little. I plan on probably on the DMS wiki. I'm going to just put up everything. Like I say, got to get somebody to help me design the 3D print files for the case. That's also going to be everything. The circuit diagrams, everything is going to be made public.
So they don't want to do a flat pack laser cut like I do? Is that all?